Namaste and welcome to yet another lecture on linear algebra through geometry. In the last couple of classes we have been looking at the solution to the system of equations Ax is equal to b, where b was not in the column space of A. If b were not to be in the column space of A, then there exists no solution such that Ax is equal to b. And we also had this what we said let us assume that the rank of A is equal to the number of columns. That means the matrix A has full rank, and then what we did is we said that we will find a representative for the vector B in the column space of A, and the representative for B in the column space of A was basically the orthogonal projection of the vector B onto the column space of A. That is what we saw. And the moment it is projected onto the column space of A, I mean you can always find out x or x star or x dagger such that Ax is equal to the representative of B in the column space of A. That is exactly what we did, and we also looked at the matrix which was called the pseudo inverse matrix of the matrix A. We looked at the pseudo inverse, and when the matrix had when the matrix A was a full rank matrix, we said that the pseudo inverse is given by A transpose A, the whole inverse into A transpose. And what Ax was actually doing, Ax was the Ax dagger that we found in the previous class was basically the projection of the vector B onto the column space of A. That is what we had. And therefore, A into A transpose A, the whole inverse into A transpose must be equal to a projection matrix, and that is exactly where we got into the idea of projection matrices, properties of projection matrices, and we figured out like how do we identify projection matrix. Given a matrix, how do we know that it is a projection matrix? That is something which we looked at in the last class, and we said that any matrix is a projection matrix if it is symmetric and if it is idempotent. We in fact proved that A into A transpose A, the whole inverse into A transpose indeed is a projection matrix. We established that they had it was both symmetric and idempotent, and then we went on to ask one more question. Say suppose I want to project a vector onto another in the direction of another vector onto another vector. A projection we saw was a linear transformation. So we were looking for what is that matrix which is going to help us project a given vector let us say u in the direction of V, and we figured out this rank 1 matrix which was basically V transpose divided by V transpose V was helping us project any vector on to the direction of V itself. And we then went on to look at a projection of a vector onto a plane which is spanned by two orthogonal vectors. We took u and v to be orthogonal vectors, and we wanted to figure out what is the projection of what is the matrix that projects. That is a question that we had, projects any vector onto a plane passing through the origin and the plane being spanned by two orthogonal vectors. And the same idea of what we did for a single vector holds good here also. So we said that if u and v are two orthogonal vectors and they span a plane, basically you have a plane passing through the origin. We said that the matrix which is going to project any vector onto the plane was basically say u transpose divided by u transpose u plus v transpose divided by v transpose v into that vector whatever that you are trying to project. Now what we are going to do in this class is we are going to spend some time on discussing the pseudo inverse of a matrix, and we will also try to look at the pseudo inverse of certain special matrices and try to understand the pseudo inverse a bit better. And once we do this, I will again go back to the idea of eigenvalues and eigenvectors. We are going to look at some interesting stuff out there. So in this lecture that we are going to do, we are going to focus on pseudo inverse and properties of pseudo inverse matrix and pseudo inverse of certain special matrices. Let us get going. Okay. So how did we define pseudo inverse of a matrix? So suppose A is an m by n matrix, real matrix with a rank of A is equal to n. That means A is a full rank matrix, that is A is a full rank matrix and let B be any vector in Rm. That means we are not looking for we are just saying B is a vector in Rm. That means it is a vector which is not there in the column space of let us say the matrix A. So, we are going to say that okay, it is going to be a vector in Rm. Now, what we are going to do is we are going to say that so Ax equal to B does not have a solution, does not have a solution if B is not in the column space of A. That means assume that we have this and assume that this is going to be the column space of A and the B vector is going to be away from here. So, this is going to be my B vector that I have. Now, what do? I project this guy onto the column space of A. This is basically projection of B onto column space of A. Right. We figured out that okay, you can find an approximate solution here or the best optimal solution which is going to minimize the error between the given B and the Ax dagger that you are going to get in the squared. So, we are going to look at X dagger to be A transpose A the whole inverse A transpose B is what we have, and A transpose A the whole inverse A transpose is called the pseudo inverse, is called the pseudo inverse of the matrix A, of the matrix A, and it is denoted by A dagger, denoted sorry by A dagger. Now, so let us look at what it means to say this A dagger, what does it geometrically mean, like to say that there is a pseudo inverse for this matrix. We will look at all that now. Okay. Yeah. So, let us look at this. So, our optimal solution is something which we have already seen, which was nothing but A transpose A the whole inverse A transpose. So, let us basically define what it is to say this A pseudo inverse. So, let us look at that. So, definition. So, the pseudo inverse of a matrix A. So, A dagger the pseudo inverse of the matrix A is that matrix which satisfies the following properties. So, what are the properties? We are going to see them. 1, A dagger B is in the column space of A transpose. Now, what does that mean? Basically, A dagger B is in the row space of A transpose. If you remember, we had this row space of A to be the column space of A transpose. So, because A transpose, the columns of A transpose is basically the rows of the matrix A, or the rows of the matrix A become the columns of the matrix A transpose. And the second is the most important property, where we are going to say that A pseudo inverse is equal to the projection matrix is a projection matrix that projects vectors in Rm onto the column space of A. So, these are the two properties that a pseudo inverse matrix must satisfy, and we have one more. So, we should look at this. So, A transpose, if you look at, I mean A pseudo inverse is an n by m matrix if A is an m by n matrix. Right. So, this is what the pseudo inverse matrix is. Right. Now, let us look at quickly some of the properties of the pseudo inverse matrix. So, what are the properties of the pseudo inverse matrix? So, let us look at that. So, what are the properties of A dagger? So, let us look at that now. So, the first thing that we want to see is we want to see what is A into A dagger into A. Let us look at that, and what is A dagger into A dagger. So, we are going to look at both those properties. So, just look at that. So, what does this product boil down to? And then what we will do is we will look at the pseudo inverses of certain special matrices, right. So, we will look at that. So, the first property is this, number 1, A into A dagger A. This is basically the matrix A. This is basically the matrix A itself. Now, the second one, the second property is A dagger into A dagger is the pseudo inverse itself. These two are very important properties that you have, that is A into A dagger into A and then A dagger into A dagger. What does this product boil down to? You see that the product of, so therefore, this A dagger A whatever that we see here, it basically it's basically like an identity matrix that we get. So, you have A into A dagger A which is giving me A and A into A dagger which is basically giving me my A dagger itself, right. Now, what we are going to do is we are going to look at the what would you say, the pseudo inverse of certain special matrices. So, we are going to look at pseudo inverse of certain special matrices. So, in fact, it is easy to prove this. You can look at this as A into A transpose A, the whole inverse into A transpose A. So, I am going to get this as A and here you will see that this is basically A transpose A, the whole inverse A transpose into A pseudo inverse. You see that these two are inverses of each other. So, you are going to get A pseudo inverse, that is easy to prove. Now, what we want to do is we are going to look at the pseudo inverse of certain special matrices. What do we mean by these special matrices? Suppose assume that the matrix is invertible, the matrix A that we are looking for is invertible. In that case, what happens? That means your A is going to be a square matrix where the column space is also column space of A and the column space of, and assume that the matrix is full rank, that is why you say it is invertible matrix. Now, in that case the column space of A and the column space of A transpose both are Rn. In that case, what happens to the pseudo inverse? So, those are the things that we are going to look at. So, let us look at some of these special matrices. So, what are those special matrices that we are going to consider? The first thing we already know, what is that? We know that if we have, okay. So, let us, the first one, suppose A is invertible, right. That means A is an n by n matrix, A is an n by n matrix. So, the column space of A invertible is, we already know that the rank is n, these are all equivalent statements. So, you have rank of A is n. So, in which case what do we have? We have the column space of A is Rn itself, column space of A is Rn itself, and the matrix A, if you see, since it is an n by n matrix, it basically transforms an n component vector to another n component vector, it maps an n component vector to another n component vector. So, basically you are going to have Ax is equal to B, where x is also an n component vector and B is also an n component vector that we have. So, that means so we have if say let us say Ax equal to B. What do we mean by this? We say that the x is basically an n component vector and the resultant vector B that you get is also an n component vector, say Rn. right, both of them are in Rn. Therefore, what is it that we are looking for? We are trying to look for, if you remember, we were trying to look at first of all we were trying to project that vector. If B were not to be in the column space of A, we tried to project that vector onto the column space of A. Now that B is an element of Rn and A is an invertible matrix, that means the column space of A has a basis which is corresponding to the columns of the matrix A. So now what we have B is already there in the column space of A. That means what is the matrix that is going to project a vector which is already there in the column space of A onto the column space of A, that is what we are going to look at. So which means the matrix that projects B in Rn to the column space of Rn, which is Rn itself, to the column space of A, sorry, to the column space of A which is Rn itself. So what is that matrix that is going to project a vector which is already there in the column space of A? It's the projection of that vector onto the column space of A is basically that vector itself, it's already there, in which case it is the identity matrix which is going to project every vector in the column space of A to the column space of A. So is the identity matrix I. Is the identity matrix I. Now what is it that we know? We already know that A transpose A. So what do? We have A into A pseudo inverse is equal to P is the matrix that projects every vector onto the column space of A, right. It is going to project every vector onto the column space of A, which means we have, and that projection matrix we have already said that the matrix that projects every vector in Rn to the column space of A, which is also Rn, is the identity matrix I, we said. So we are going to have A into A dagger to be equal to the identity matrix. Now what is A dagger? We already know what is A dagger. So let us look at what is it. So we know that any matrix into, if you have a product of two matrices to be I, we know that one is going to be the inverse of the other. So in which case, in this case, the recall, let us do this. So recall the A dagger, the pseudo inverse, produces, or it provides, the A dagger provides the best solution to Ax is equal to B, and therefore what we have here is, in this case, which implies A dagger is equal to A inverse itself. So what are we going to say? If A is invertible, so if A is invertible, the pseudo inverse of A, the pseudo inverse of A is the actual inverse of A, the inverse of A itself. So in this case we have, let us write this. So for A invertible, A dagger is equal to A inverse. Yeah. Now, we will look at the other one. What is this? Suppose we actually had the other that is exactly where we started with. So, case 2 or okay, let us look at the next matrix. Suppose A is an m by n matrix with rank is equal to n. Rank of A is equal to n. Now, what does that mean? This implies A has linearly independent columns, right. This implies A has linearly independent columns, and we have already seen this. If A has linearly independent columns, we have seen that A pseudo inverse is nothing but A transpose A the whole inverse into A transpose. So, we have already got that, right. So, in this case A pseudo inverse is equal to A transpose A the whole inverse A transpose. The third case we are going to look at is when we have A has linearly independent rows, right. Suppose we have A is a matrix, A is m by n matrix with linearly independent rows. Now, what does that mean? Linearly independent rows. Now, that implies rank of A is equal to m, and in this case A transpose is an m by m matrix and invertible. Right. If this is a case, we have a m by m matrix and it is invertible. So, now what is the so let us look at this. So, in this case, in which case to solve A x is equal to B, we again do the same business projection and stuff. So, we look at all that. So, if we work out and we try to find the, I mean we see what is the, okay, let us see what actually happens here. Okay. If A is an m by m matrix and the rank is invertible, let us take a simple case where A is let us say 2 by 3 example. A is a 2 by 3 matrix and rank of A is 2. Now, what does this mean? This implies A is equal to let us say A11, A21, A12, A22, A13, A23, though this is basically a 2 by 3 matrix. Now, as we have already told that the rank of A is 2, that means out of these 3 columns that we have for A, there are 2 linearly independent columns that we have. So, this is basically of the 3 columns of A, there are 2 linearly independent columns we have already proved that the row rank is equal to the column rank. So, there are 2 linearly independent vectors we have, and Ax is equal to B implies a 3 dimensional vector x is going to get mapped to a 2 dimensional vector B, and therefore the column space of A is already the entire, let us say Rm. So, the column space of A, this implies column space of A is Rm, right. You have a vector which is there in Rm and you want to project that vector back into Rm. So, what is it that you want to look at? So, the projection is going to be again an identity matrix. So, we are going to say this. So, thus the column space of A, thus the column space of A is Rm, and what are we going to say? We are going to say that the projection matrix that projects B in Rm to Rm is the identity matrix M cross M, identity I M cross M. Now, we have already said A transpose is an M by M matrix, it is invertible, and this has also the rank M, rank is equal to M. So, what we are going to say is A transpose is invertible, therefore, we are going to talk about the pseudo inverse of this matrix. So, the pseudo inverse of this matrix is basically given by the following. So, we have A pseudo inverse is equal to A pseudo inverse is equal to A transpose into A transpose the whole inverse, if rank of A is equal to M. Right, if that happens, then this is the pseudo inverse. Now, we are going to look at the next one. So, what are we going to conclude? We are going to conclude that if A has linearly independent rows, then A pseudo inverse is basically A transpose into A transpose the whole inverse. Probably you can even prove this. You are looking for Ax is equal to B, and what you do is you figure out that since the rank of the matrix A transpose is equal to M, that means your what we do is we are going to say that you express any vector. Okay, let us do this. So, I mean just outline of the proof. We have Ax is equal to B. Now, since rank of A is M, rank of A transpose is also M, express X is equal to, let us say, A transpose Y. So, what we have? We have A into A transpose Y is equal to B, and basically X now is in column space of A transpose. So, you have A into A transpose Y is equal to B. Now, A transpose we already saw that it is invertible. So, what are we going to have? We have this implies Y is equal to A transpose the whole inverse B. we wanted to look at x is equal to A transpose y. So, x was equal to A transpose y. Therefore, what we have x is equal to A transpose into A transpose the whole inverse B. So, this is basically my, let me put this as x dagger. So, I have A dagger to be equal to A transpose into A transpose the whole inverse is what we have. And the last one is the most interesting one. Suppose, let us look at this. Suppose A itself is a projection matrix, Now, what does that mean? That simply means if you want to project any vector onto the column space of A, use A itself as the projection matrix, right. So, what does this mean? Two things. The first thing is A square is A, and second thing is these are the properties of projection matrix. A transpose is equal to A. Now, what we have is we want to find out the pseudo inverse of the matrix. Therefore, the matrix that projects vectors onto column space of A is A itself. So, we already know that properties of the pseudo inverse matrix. We know that A pseudo inverse is equal to the projection matrix, in which case here A pseudo inverse is basically A itself. This projection matrix P projects every vector onto the column space of A. So, I have A transpose is equal A dagger is equal to A. So, what is it that we have? So, I will take this out, I will say A into A dagger minus A is equal to the 0 matrix. Therefore, what we have? We already have this A into A dagger B minus AB is equal to 0 for any vector B, which implies A dagger B minus AB. So, if you look at this, this is of the form Ax is equal to 0. Therefore, this is in the null space of A, for any B. But if you see, this vector is also there in the column space of A, because A transpose is A. So, what we are going to say? We are going to say that but this vector is also in the column space of A transpose, because A dagger B and AB is equal to, since A and A transpose are the same, AB is equal to A transpose B are all in the column space of A transpose. So, we already know that the row space or the column space of A transpose and the null space are orthogonal complements to each other. Therefore, what we have? We have A dagger B minus AB is equal to 0, because since call space of A transpose and null space of A are orthogonal complements, we have A dagger B minus A B is equal to 0, which implies for all B, and therefore, this implies A dagger is equal to A itself. So, if A is a projection matrix, then the pseudo inverse of A is the matrix itself, the matrix A itself, right. So, in this lecture what we saw is we looked at the various properties of pseudo inverse matrix, and we also looked at the what would you call, we looked at the pseudo inverse of certain special matrices, matrices which are invertible, matrices with linearly independent columns, matrices with linearly independent rows, and then we said that matrix which is actually a projection matrix, that means a matrix which projects every vector onto its column space itself. So, that is the kind of matrices that we looked at, and in each of those cases we figured out what the pseudo inverse of each of the matrix are. So, in essence what we have done is we basically looked at various interesting things, like we started off looking at Ax is equal to B, where B was I mean we wanted to solve the system of equation Ax equal to B, where B was not in the column space of A. And then what we did was we basically figured out the best optimal solution by projecting B onto the column space of A. We figured out that there is something called a pseudo inverse, and then we studied the properties of projections and all those things, right. And we figured out certain special matrices for I mean the pseudo inverse of certain interesting matrices. So, next what we do is we are going to go ahead with a little bit in details about the eigen decomposition. I am going to do this eigen decomposition as the next lecture, and from there on what we are going to do is we are going to look at certain interesting properties of real symmetric matrices, and we are going to look at what is the, suppose I say that there is a matrix A which is going to transform any vector x to another vector, let us say B. What is it that I am going to, I mean what does it geometrically mean? So, that is something which we are going to look at in the next lecture, where I am going to get back to the idea of eigenvalues and eigenvectors. I am going to look at diagonalization of matrices and so on. So, that is the agenda for the next class, and I hope we understood the idea of pseudo inverse and stuff. So, essentially we are going to eigen decomposition followed by singular value decomposition and stuff. So, the next lecture we will focus on eigenvalues and eigenvectors. Thank you.